Thank you everyone to be here with me. It's a pleasure for me to moderate this roundtable about MOF as a powerful framework for pollution remediation. I think is like a commitment for us as a scientists, for what we know and for our knowledge and the tools we can provide to the world to explain and talk between ourselves about the way we can actually stop environmental pollution. So just because I don't like acronym, I will briefly say what MOFs are. So MOFs are like a metallic organic framework, and they basically are like fall into a class of crystalline inorganic hybrid porous material that they have like a lot of freeing properties, and they can be used especially for their property about host gas chemistry to selectively and with high efficiency capture like pollutants in water, in the air, and the environment. The last like 10 years, 50 years, basically, they show that they have way better performances with respect to capturing pollutants in the environment with respect to common other materials or techniques that have been used. Now it's a pleasure for me to share this roundtable with three amazing scientists that are women and are very successful. I'm very jealous of their CV, so it's a pleasure for me to introduce them. So I will read now because I don't want to make any kind of mistakes. We have as first speaker, Tania Patiño. So Tania, she's a Marie Curie Fellowship from the University of Vergata. She is doing a visiting research period here in Barcelona at IBEC, where she basically did her PhD in Barcelona. She has a lot of background in biomedicine, biomedical, and now she's working for DNA-based nanomachines. So it will be very great to see what she's doing and how this can be used for MOF and for pollution remediation. Then the second speaker is Leyre Gómez. She's a PROBIST postdoctoral fellowship here at the ICNTU in Barcelona. And she's a chemical engineering with a degree from the University of Zaragoza. And she's basically working on the integration of metallic organic framework for photonic nanosensor for environmental monitoring. Myself, I'm basically working not using MOF, but for like detection of pollution in water. So it will be great to see how our technology can mesh up with mine as well. And then last but not least, we have Cristina Sáenz de Pipaón. I hope I didn't mess up the surname. So she's like a very great example of like how when you start academia doing the PhD, then like your job is not just in academia. In fact, she did a PhD, then a postdoc, then she was a CEO over on startup, and that now while she's working to as well shorten the TRL between the path from academia to industry, and as well in MOF for selectively capture CO2. So all the speakers will have more or less 12 minutes to do their talk. So I hope you can be a bit shorter in time so we can actually discuss between us and with the audience. So the first talk is on Tania.
Yes. Okay, perfect. Yeah, so I would like to first start thanking the organizers for this super exciting roundtable and for having me here today. I will talk about a collaborative project that came from a BIST Ignite call, where I am co-PI together with the group of Daniel Maspoc at ICN2. And what we are trying to do with this project is to develop what we call MOFs. Okay, so this is a very nice collaboration and a lot of synergy between the two groups and within BIST, and we are super happy to share it today with you. So in our group at IBEC, during the last years, we have been working on developing what we call micro nanomotors, which are micro nanostructures that are able to move in fluids And we are using this for biomedical applications, which I will not talk today because it's not, it doesn't fall in the topic of the roundtable, but also we can use these micro nano machines as microcleaners. And in this regard, we have some experience in the field of cleaning in different ways pollutants. We can use catalytic reactions to degrade pollutants. We can also capture some bacteria. And using graphene, we demonstrated that we can also capture heavy metals from water. So these are opening a very exciting new class of materials for the field of environmental remediation, and a lot of different systems have been already also published in the literature by ours and other groups, where what we do is to use this self-propulsion to make the particles more efficient in collecting and cleaning these types of water. And how we achieve to move particles at the nanoscale it is not trivial, because at the nanoscale you have very high viscosity. I mean, the viscous forces are more important than inertia. So then it's not easy at all. And what we do is to try to learn from nature. And what nature does and teaches us is that you can actually harvest chemical energy using catalysts. And then with these chemical reactions, it is possible to generate motion. In artificial systems as ours, we can do this, for example, by developing this type of tubes which are have an inner layer of platinum. Platinum acts as a catalyst to degrade hydrogen peroxide, and this in the cavity, some bubbles can be generated, and these bubbles produce this thrust force that allow these microswimmers to swim and move in fluids at the macro nanoscale. We can control them, we can recover them if we add some magnetic layers, so this is very exciting. Additionally, we can continue learning from nature to engineer other types of micromotors which rely not in metallic catalysts, but in more maybe sustainable or biodegradable and biocompatible catalysts, which are enzymes. Enzymes are the proteins that we have in our body. In the human cell, I put here, you have more than 1,300 enzymes. In the human body, a lot of them. So we have a lot of versatility that we can explore here, and we can degrade different substrates that we are interested in. So what we do in our group is also to take these amazing catalysts, which are enzymes, we coat them on the surface of our particles, and with these chemical reactions, we are able also to develop micro nanoswimmers. So an idea that came with this project is like, okay, we know how to make microswimmers, but if we wanted to work in environmental remediation, we need a high loading capability, right? So as I explained to you, you can degrade pollutants that are in the water with our chemical reactions. We can also absorb the components on the surface of the particles. But what if we use the unique and exciting properties of motors, right? That is the expertise of the group of Daniel spoke as well. So with this kind of systems, we can have a highly porous cavity. We can even fine-tune these pores. So as Alfredo was saying, metal organic frameworks are this class of materials which consist of metal frameworks organized by organic ligands. And we can have very controlled shapes, homogeneity of the sample, and also we can have a high degree of control over the porosity of the material, where we could encapsulate and protect our catalyst. So as I explained you, we are interested in using enzymes, so it's necessary to have a scaffold where we can protect them and also that they can fit, right? And then we also need to have, or it would be amazing to have available other pore size, so to encapsulate other type of pollutants or contaminants that we want to collect from the environment. So this is the idea behind the project. And so far we managed to, well, in the group of Daniel Maspot, they managed to synthesize these super nice MOF structures with a method that they use that is ozonolysis to create these mesopores. These are the MOFs. They are super nice. They have very homogeneous shapes, sizes. We did a lot of characterizations. Then what we wanted to do is what I told you. So we want to rationally control the porosity. So we are aimed at creating mesopores that were able to host catalase as a model enzyme, catalyst. And then we also wanted to create these micropores that would be able to absorb pollutants. We checked whether this method would be suitable for this. And here you can see that we, after ozonolysis, we are able to encapsulate catalase, which is this green signal that you see here. And the red signal comes from rhodamine B, which is a molecule that is fluorescent, and it's often used as a model molecule as pollutant, or also for drug delivery applications. As you can see here, rhodamine is a lot more encapsulated than catalase. We attribute this to the size of the molecules, but in any case, the exciting thing is that we managed to have both in the same system. And then we did a lot of optimization for the particles to move. We studied how the presence of surfactant that will allow this bubble generation makes our motors move. We were studying how different encapsulation times of the catalyst affect their motion. And the exciting thing is that we managed to have these motors moving. And we can, so in the end, we can have both the catalyst, the pollutants, the pores are available. So we could even further design this for further applications. So, well, as a summary, this is our system. We have managed to encapsulate the catalyst. We managed to also have some pores to collect these undesirable molecules that we want to clean, for example. And with the active motion, this is enhanced because the particles can go swimming, and we could use them for a more efficient way of, or what we call a new generation of smart and sustainable microcleaners. Okay.
So now I think it's Leyre to talk.
Yeah, good morning, everybody.
Morning.
So first of all, I would like to say that I'm really happy to be here in this roundtable. So thanks the organizer for the invitation, and also thanks Alfredo for the introduction. So as he said before, my main topic now of research is the integration of MOFs as specific receptors in optical nanosensors for environmental monitoring. And I guess we all agree on the versatility of the MOFs and their capability for separation or storing. That can be pollutants, of course. So we can also use them as specific receptors for defined analytes. I guess we also agree that we are getting our air and water more and more polluted every day. So it's necessary to take actions on these pollutants remediation. But it's also really important to have the possibility to monitor in real time the status of the water and the air we're breathing. So like this, we can know exactly the amount of contaminants we have at the moment, and that allows us to take actions if necessary, okay? So in order to make a sensor, we need this specific receptor that in our case will be the MOFs. And then a transducer, we transform into a measurable signal. In our case, at ICN2 in the group of Professor Laura Lechuga, we work with photonic nanosensors, which working principle is based on measuring local refractive index changes in the sensing area. Okay, so if we combine the two areas of expertise, we want to make a highly sensitive sensor, robust, that allow us to measure in situ and in real time to do this pollutant monitoring, okay? So a couple of years ago, there was this collaboration between the group of Professor Laura Lechuga and Professor Daniel Maspok, which is an expert on MOFs, as Tania mentioned before. And they made this sensor for CO2 detection, where a miniaturized CIF8 was integrated in a bimodal waveguide. And this opened the way to this new research line that I'm leading currently. Today, I want to give you an overview of this specific project, which is a BIST Ignite project that I was awarded in the last call. And it's a collaboration between ICN2, myself, and ISIC the group of Professor José Ramón Galán Mascareros. And here we want to do an optical sensor which has the possibility to detect enantiomeric molecules. And these have a really important sense in pharmaceutical companies in drugs. Why? I guess everybody knows the case of thalidomide. It's a drug that was used for pregnant women to avoid the nausea, but it has two carrier molecules, and one of them was in fact the drug, but the other was making undesirable effects on the babies. And this happened with a lot of drugs. Another example is, for example, ibuprofen. When we buy an ibuprofen pill, we're taking a mixture of enantiomers. Why? Here we have not a problem of making side effects. The main difference is that the one of the ibuprofen molecules is much more active than the other, but because of the expensive treatment to make the separation, it doesn't make sense. So we take a mixture. So for pharmaceutical companies, for example, or even to have this control, of pollutants, in this case, drugs in our rivers, will be really important to know which kind of molecules we have there. So the project started with these publications of the group in ICFO. They synthesized this MOF called TAMOF1, which is a rhombidodecaedral shape with electrons, and they use it in a liquid chromatography column, and they were able to separate carrier molecules. For example, ibuprofen, but also with other different drugs. And it's a MOF really stable in different solvents and even water. So we have this as our specific receptor. And on the other hand, we are using an optical sensor LSPR, localized surface plasmon resonance. Here on the left, you can see the real image of our setup. We're working in continuous flow. And what we have is a gold substrate inside there, which is giving us a signal versus wavelength, which is the plasmonic peak. When we change something on the surface of this gold, we see a change on the wavelength, and our sensor is going to work by detecting this different wavelength versus time. So, okay, we have the specific receptor, we have the transducer, we know how it works, but now the main question is how to mobilize this receptor, this TAMOF1, on the gold sensor. First thing comes to our mind, and the easiest way could be spin coating. So that's what we tried first, but the results weren't good enough. So we see that the attachment is really weak. And here on the graph in the right, you can see the signal is decreasing, which means that with time and with measurements, we are removing things from the surface. So we cannot use this sensor. Next step we did was to do the MOF on the gold. Here you can see a real image on the lab. So the gold, you cannot see it, but it's underneath this white holder. It's placed upside down in order to be sure that what we are growing there is because growth, and it's not because there's precipitation on it, okay? So here I want to show you some images of this in situ growth of the TAMOF1. And the different images and the numbers means how many growth layers we have done in each one. So here we are dealing with different problems. So for example, 1 and 2, we are keeping the plasmonic peak of the sensor, but the stability of the layer is weak. And it seems we don't have enough material for the sensing activity. While 3 and 4, the layer is stable, but because the thickness increases of the MOF on the gold, we are losing the plasmon peak and we cannot use the sensing activity of the gold. Here you have an example of a bare gold and 2 layers TAMOF1 for different flow rates with ibuprofen, and we can see that the differences are not significant. So with this system also we were not able to conclude our work. So we thought next was to make like a pre-chamber, a separation, so to do like a tiny chromatographic column just before the gold sensor. Here you can see in the image. So we do a pre-treatment, so our ibuprofen sample goes through the chamber, and because of different retention time, we will see in the gold sensor the difference between one chiral molecule or the other. And here on the right, you can see the difference between per gold or using this pre-chamber. And here the differences are more significant. Here we can see that the behavior is different. We have one chiral molecule or a mixture of them. And just to conclude, I would like to tell you that with this process, we have managed to detect if we have one type of ibuprofen or the other, but we were not able still to quantify how much of each one we have. So we are working on optimizing this for better results. And also we are working on different projects of integrating different MOFs in different optical sensors for detecting different pollutants that could be, for example, heavy metals or pesticides or drugs, as I have been explaining during this presentation. So thank you all, and let's questions.
Thank you, Leyre. Yes, we'll keep going, collecting the questions, and then we'll discuss later on all together. Now it's the turn of Cristina.
Hi, good morning. Thank you very much for inviting me to be here. Thanks for the previous presentation. I think that Leyre explained part of the things that I'm going to talk, but it's perfect. So let me start my presentation and let's start talking. I believe in the power of storytelling. When I want to translate or to communicate something, I believe that the good thing is to tell a storytelling, because you will keep the concept for you and you remember that. So today I'm going to talk about the storytelling of Orchestra Sci, that is a spin-off from the ICIQ. So let's check. Orchestra Sci is working with CO2, and I think that all of you knows CO2, but CO2 is not only known because it's responsible of part of the climate change. It's also a part of biogas, that is a renewable source of energy, and it appears in numerous industrial processes, but it's also a product that can be commercialized. So if CO2 is so important, there are several technologies able to separate carbon dioxide, and all of them have advantage and disadvantage. But if it's possible, industry prefer technology, membrane technology, because it's a compact technology, it's easy to install it, and the maintenance is very easy to do. But they present a problem. That is that they need to work at high pressure. Working at high pressure means that we have to use them, or we can use them only in application that occurs at high pressure. For example, biogas upgrading, but we cannot use conventional membranes for capture carbon dioxide emission to atmosphere, because that occurs at atmospheric pressure. Until now, Orchestra has the license to use TAMOF, a metal organic framework that we call TAMOF, that has been patented, and the production has been scalable. And with this material that is very selective to carbon dioxide, we incorporate that into membranes to obtain highly selective membranes able to separate carbon dioxide from other gases. And in doing that, we increase the selectivity of the membranes, we reduce the pressure operation, and we increase the robustness. This is the same TAMOF, the same metal organic framework Leyre was talking previously. So there is a market for this, yes. We can use our highly selective membranes for biogas or natural gas upgrading to purify the biogas and obtain biomethane, or in chemical process. In that case, we are reducing the operational cost because we are working at atmospheric pressure or low pressure and not at high pressure as conventional membranes. Or we can use our membranes to capture carbon dioxide emission to the atmosphere. all of them are markets that are prioritized by the European Union to fight against the climate change. So what is biogas upgrading? Because I'm talking about that, and I'm not sure if you know. If we let organic waste rot in a digester, we will obtain biogas that is a mixture between methane and carbon dioxide. So we can burn the biogas to obtain heat or electricity, or we can go one step further. That means that we can purify the biogas by taking out the carbon dioxide and obtain biomethane that can be used in cars, or mobility, in transport, or even injected into the gas grid distribution. This market is a market that is growing very fast. In Europe, the number of biogas upgraded plants has doubled in 2 years, and it's a market that is growing. And this is only biogas upgrading market, but with an appropriate technology, we can consider that our market is all the biogas market, not only the upgrading, because we can convert all the biogas in biomethane. So this is a market that is moving, has a share of millions. I was talking also about CO2 valorization. CO2 is a greenhouse effect gas that is emitted, and there is something called right emissions, and companies will have to pay for every ton of carbon dioxide they emit. Like 2 years ago, the price for every emitted carbon dioxide ton was about €5, but right now it's around €25. So companies are looking for a solution to avoid these carbon dioxide emissions. And what can we do after avoiding these carbon dioxide emissions? There are several uses that can be given to the carbon dioxide. It has a market, and carbon dioxide in the market can be bought at €140 per ton. So this is a perfect example of circular economy in which we are avoiding the carbon dioxide emissions, so the companies don't have to pay right emissions. And we are converting this waste in a new product that can come back to the market and commercialize. So let's use an example, because sometimes it's better if you make numbers. Imagine that there is a company that is emitting 18,000 tons per year, and a ton of carbon dioxide is like a cube of 8 meters of age. So at the end of the year, this company will have to pay like €500,000 per emitting this carbon dioxide. Let's imagine that this company installed a technology for capturing the carbon dioxide. And instead of emitting 18,000 of tons, it only emits the 20%. In this case, the bill reduced from €500,000 to more or less €100,000. But what can we do with the other carbon dioxide? Imagine that they can sell the 70-100%, and there is a market that is oversaturated with carbon dioxide, and instead of selling that at €140 per ton, they sell at €40 per ton. So at the end of the year, they have gone from paying €500,000 to gain €500,000. Interesting, I think so. So this is the limit that companies that are devoted to carbon dioxide capture technologies has to make the business profitable. So all this project started in 2017 with the patent in the ICIQ. And the patent comes from Dr. Galán Mascaro's lab, and Neus Corella was the doctor that was working in the project. And they saw the potential of this material and decided to talk to the industrial property unit with Fred Rattel, Dr. Rattel in ICQ, and they saw the potential of this technology and decided to patent that. So we have a material that was able to separate carbon dioxide from other gases. And all of this is probably graphics that you can understand better than me, because when I told to investor what I use, and believe me, is that. I say that we have a material that it modifies the velocity that gases go through it. And you see, the carbon dioxide takes longer to go through the material. So we thought that we have this material and could be interesting. The IP unit said that it will be interesting to patent that. But we spent like 1 year in different acceleration programs, talking to companies, talking to the market, and we realized that it was better that the company preferred that the powder was in membranes because they have other advantage. So in these acceleration programs, we refine and we define our business model that is as important as the technology. And we spent 1 year developing this business model. After that, we founded the company. The company is founded by 5 entrepreneurs, by 5 co-founders, and it's also participated by ICFO and Ukraine. We also have at this moment 1 investor that was InnoEnergy, that is a European network for energy. After that, it comes escalation process that it took like 1 year or 2 years, that it was financed by an POC project from the European community. And we have escalated the production of the material from grams to kilograms, and we have escalated the production of the membranes. We installed a pilot at the end of 2019 with the help of Fundación Repsol and Suez. So this is very important to look for clients and to talk to them. And during this year, we are reformulating the structure of the membranes and looking for other alternatives because we are pivoting. So we expect to have a new pilot ready for be tested in 2021. And we will buy our first plant in 2022 and with the help of European financing, I hope. So all of this was, I wanted to transmit you that, as you can see, entrepreneur is not easy, but I believe that there are really good ideas and really good materials and patents in the BIST. So if you feel that entrepreneur is very complicated, that's true, but you only need an idea that you want to go to bring to the market. You can have the best idea in the world, but there is no market. Please don't do that. And you have a lot of paths to go through that. If you choose a good team, life will be easier. And if you are fully committed to the project and you believe in the project, life will be even more easier. But if in spite of all of this, you doesn't reach market, never say that you have failed, because you have another opportunity to try again. So this is more or less what I wanted to talk about. And there you have my email. So if you have any question or you feel that I can help you in any way, just please let me know. Thank you.
Thank you, Cristina. Very interesting and inspirational. More or less 3 similar talks, like driven from the same topic, but different one from the other one. Like the first 2 more like from the research part, like the last one, how to actually make it something true from the lab to the market. So we have 1 question from the audience, but before starting with that one, I would like to ask like 1 question myself, just out of curiosity. Like what happens at the end of life of the MOF? Like how do you dispose of the MOF, or like your membrane with the to capture CO2, or like the MOF robot? Like you had this tool, right? You use it to capture heavy metals or to capture CO2, right? But this like tool has a shelf life. So it will last like 1 day, 1 week, 1 month, 10 years, 20 years. Like what happens at the end? So like, is it worth it to use it like in the full life cycle analysis of the product, or like it has like a lot of benefit, but on the other side, that maybe is not seen as a lot of like cons?
Well, this is something that happens with MOFs. You have to look for the stability and the robustness. I think that Leyre can talk more about me about the chemical structure of the TAMOF, but the MOF that we are using is very stable. And when you incorporate the TAMOF to the membranes, we are aiming for life of membranes above 10 years. So I think that is pretty nice. Of course, you have to be very careful about some contaminants that can damage your membrane and your TAMOF. But in all the plants, there are previous filters to eliminate that. So regarding to your question, the TAMOF that the MOF that we are using is very stable, and the lifetime we are aiming to be longer than 10 years. So I think that is pretty okay.
Yeah, that's great. Then a question from the audience, I think it was for Tania, is, are there limitations to scaling up stability and health safety issues with respect to enzyme MOF-based nanomotors for real-world application?
Okay, so for the part of scaling up, I think that my colleagues maybe can help you more because it's not my expertise. So we work more in the developing these structures, seeing if they are able to encapsulate pollutants, providing them with motion, which is not trivial. In our case, we in the project, this is one part, but the other part, we are also aiming at trying to use this as drug delivery carriers. So what we are using is a kind of biocompatible MOF and also catalase as long as we don't think that it can be harmful. It depends on the dose, on the fuel that you are using, on the products you are generating. Of course, you can control this very well. And since one of the aims was to use it for biomedical applications, I think that we should be kind of safe. Of course, one has to do all the required studies, but I think we have potential that this is not a very strong limitation to our system. And for the scaling up, I don't know, maybe Leyre knows more about this.
Well, about scaling up, probably Cristina knows more because she's really in this industrial path. But from my point of view, well, I am a material scientist and I have also experience on scaling up nanomaterials. Not specifically MOFs, but other kind of nanoparticles. And of course, it's not easy, but normally it's possible. So by reactors, or I was working in a continuous flow, so that's even better because you don't have problems from these batch to batch differences. But it just requires some time in the lab and adjust all the parameters because it's not just so easy as just, okay, increase the volume and that's all. But with spending time in the lab, I think it's durable for any kind of MOF and other kind of nanoparticles. But Cristina will know more about that for sure.
Well, in the opinion of a physicist that has been working with chemists for a long time, the answer is always, it depends. Because it depends on the material. Not all the metal organic frameworks are going to be scalable, but some of them can be. We were very lucky because this MOF can be escalated. In fact, we have subcontract other chemists, other pharmaceutical companies to produce kilograms. So it's perfectly scale up. But to start scaling up, we will help it by the CESOL area that is in ICQ, and they have a lot of expertise in scaling up compounds. So I invite you, if you have any doubt about scaling up any compound, to talk with them, because they were the ones that help us. I think that not all the metal organic frameworks can be scalable. But for the ones that can be, they have very interesting properties, and we have to take advantage of them.
Perfect, thank you. And I have another naive question. So if you have a spillage of MOF while manufacturing them from the industry, do you have something you can use to capture those, like using MOF for MOF pollution? I don't know how to say that. So you are synthesizing this MOF, right? And there is a spillage of them in the water, in the sea, in the river. Well, doesn't matter. Do you have like a technology to capture them efficiently?
Well, the MOF that we are using is not is made from an amino acid and copper, so it's not dangerous. It doesn't matter if you spill it. So it's not a problem. You can touch it, and in fact, the membranes, they have been in my lab and in my table for months, and it's okay.
No, I mean like an outbreak of like one that can happen from like dye industries, colors, like that there's some spillage of colors in the river. Like you have somehow something bad happen, and there is like all the MOF you are producing that they go like in the river somehow. Do you have a technology to recover them, like to take them off or to clean the water?
No, I think that no, we don't have, but anyway, it's not good to be harmful to the environment. So let's look the bright side of life.
Yes. Then I was just like a question now, if exists MOF to recover MOF, just that. Okay. Then maybe the last questions. Do you think in how much time this technology can change the world? Like that can really make an impact?
For us, I hope that we will be ready to be in the market in 2023. So we need 3 more years. I'm so sorry. I would love to be in the market already, but it takes a long time to scale up and to test and to find the right proportion, and going from the lab to the market is not an immediate process.
Yeah, I would like to add that maybe also in more early stage research as we are, I'm seeing that every now and then we see more MOF structures. So we are working also in material science, engineering new nanomaterials for cleaning, to cure diseases, to detect things. And I think that this is something very exciting, what the unique properties that we have with these materials, the controllability. We can do many things, which is really difficult to achieve with other types of materials. So I think that, as Cristina says, maybe for scaling up and see some impact in society, economy, and this, maybe we need to wait a bit. But I think that we are already seeing a change, no, in the field of nanomedicine, nanotechnology. I see every time more efforts using MOF and collaborations, and I think that they really help in a lot of different fields. So they are very versatile and very unique. So I agree that this is changing something.
Okay, I have another question from the audience as well, maybe the last one. So if you had to place your CO2 capture membrane in the top of an industrial chimney, how long will it survive? Will it degrade due to heat? How long will it take before it saturates?
Well, obviously, we have to clean some part of the gases before going through the membranes, and we have to cool down because the membrane will be stable around 100 degrees Celsius degrees. If we go at higher temperatures, it will degrade. So if you clean up the gases and if you cool down the gases, principle, there will be no problem. The membrane will not be degraded. There are some compounds that can damage the membrane, but we can recover the membrane. For example, the water decrease the selectivity of the membrane, so it's necessary to remove the water, and in some water goes through the membrane. You have to dry the membrane again. You have to activate the MOF again. So in principle, if you work under the condition that we specify, the membrane should not be degraded. And the good thing about using membranes is that it will not saturate. If you work with only the powder that I showed you the image, using the powder, you have to work by pulses, But if you work with membranes, they will not saturate. This is why we choose to work with membranes, because for industry, it's better to work in a continuous flow. If you work just by using the powder, you have to go to work with by pulses, and the industry doesn't like that very much. So in membranes, it doesn't saturate, because what MOF does, it retains the carbon dioxide, but it doesn't absorb the carbon dioxide. It only changes the velocity, diffusion velocity through the material. So this is something really unique.
Okay, another questions from the audience. For how long have there been investigations considering MOF technology, specifically applying it to sustainability processes and environmental friendly technology? Is it very new?
Well, I will take the
Yeah.
the question, and I hope my colleagues can help me later. For me, it's a new research line, because before I was working with inorganic nanoparticles of gold or even perovskite crystals. So for me, it's really new. But I know that this field of research is not completely new. I say that it started yesterday. I don't know, maybe it has been on for 10 years, maybe. I don't really know. But it's true that during the last years, there has been this big development. Like everybody is willing to work with the MOFs for the versatility that they offer. So during the last years, like everybody's trying to find the applicability of them, because we already know their versatility. So we are trying to apply them.
Perfect, thank you. Well, I think now it's almost the time for my favorite part of the conferences, like lunch break. So thank you again to Tania, Leyre, Cristina for your time, for everyone like uploading the questions, and for everyone just listening here, and like to BIST to organizing it. And then we will be back with the conference at 3 p.m., I guess. So thank you again. And it was amazing just to talk with you and knowing you. Like, I hope we can keep in touch or maybe collaborate in the future. Who knows? Thank you again.